Hi everybody, this is David Paul, and today we're going to talk about electrocoagulation. Specifically, we're interested in pretreatment to RO. This is not common at this point, so this isn't something that you're going to see a lot of electrocoagulation in front of an RO unit, but there's some interesting aspects and we wanted to make sure that you're aware of this technology. This is going to be a 40-minute presentation. I'll give a brief introduction, and then Judd and Scott, I'll introduce them in a moment. They're going to provide the details. Then we'll have 15 to 20 minutes of question and answer. So just type your questions into the questions box, and then we'll handle all of the questions at the end of the presentation. So we're recording this presentation. It'll be available on our website starting tomorrow. We'll also send you a thank you email for attending with a PDF of this presentation. So even though you don't have the PDF right now, you'll have it tomorrow. So just sit back and absorb this interesting information. So the two people discussing EC, electrocoagulation today, Sundyne Enterprises and Pal Water. We do not have, David H. Paul Inc. does not have a financial relationship. So we're not endorsing this. We're not telling you about this technology because we're going to get any financial gain. It's just something that we were interested in. So we figured there are other people that are interested in this. So we're presenting this webinar on EC. So I've been in water and wastewater treatment for a very long time, consulted in many plants. The two gentlemen that will be talking about EC, Judd Sundyne, will give a presentation directly after me, and he's been into the industry for a long time as well, working with EC since 2003. And then Scott is the inventor of the large flow EC chambers. He has patents in the US and around the world and manufactures the EC units and complete water systems. So he'll be coming in for the question and answer period. So the reason that I'm interested personally, the reason that we started talking with Judd and Scott was that RO fouling is a big problem with the reverse osmosis units. And we define fouling as you read here. That is basically due to suspended particles or sticky, oily things that can stick to the membrane and or the feed water spacer. It can be a very large problem. We see here on the left fouling on the surface of the membrane, on the right fouling of the feed spacer, and sometimes it's in both places. Many things, many suspended particles can foul an RO unit, and these can be very problematic. They can be a real issue trying to keep an RO unit from fouling and not having to chemically clean it too frequently. So currently, if you look at fouling by particle control, media filtration, cartridge filtration, and membrane filtration are the most common today. So that's to remove as many particles ahead of the RO unit as we can. Well, this electrocoagulation does some things that in talking with Judd and Scott was of interest to me. So we asked them to come on this webinar. So again, I just want to mention this and probably will mention it again. This is an emerging technology for RO. We're not endorsing this. We're not saying go out and get EC because it's going to solve all your problems. But we're saying this is a technology that is potentially a fouling control technology that maybe is worth you taking a look at. So just very quickly, electrocoagulation is electrically driven coagulation. Now, if you've been in water treatment for a long time, you probably know about coagulation, flocculation, sedimentation that you have in clarifiers. So coagulation is where we're taking stable colloids and turning them into unstable colloids so we can get them to agglomerate, come together, because they don't want to come together in their natural form because they have a net negative surface charge, and this includes particles that are alive, like bacteria and viruses. So a stable colloidal particle is a particle that with a net negative surface charge, and because they're like charged, they don't like each other, they're not attracted to each other, so they stay separate. And they bypass all of our filtration steps in front of the RO unit. An unstable colloid is one where the surface charge has been partially to completely neutralized. So we see here positive and negative charges. So now these particles can come together due to van der Waals force, and these then are attracted to each other and they can agglomerate or coagulate. So now these particles will be filterable or settlable. Well, it's very common today to use chemicals to make this coagulation process work, either injecting aluminum sulfate, alum, or ferric chloride or ferric sulfate. And that then, the precipitation of the iron and aluminum on the surfaces of these particles partially neutralizes them. Well, in electrocoagulation, you're getting the aluminum and the iron from plates, from metal plates in the unit, and you're using DC power to produce an anode and a cathode. And the electrical potential difference, that's the driver, and the aluminum and the iron ions are going to be given off. So there can be lots of plates. They're located about 1/8 of an inch apart. So you start out with an anode and a cathode, putting these plates in between. The feed water enters and exits in between the plates. Here are just the chemical reactions for those of you that are interested in, where the iron comes from and where some of these chemical reactions occur. This again is all going to be in the PDF that you'll get tomorrow. So if you're interested in the chemical reactions, we're giving them to you here. But essentially, either the anode and cathode are going to be made of iron, Fe, or aluminum. So if it's an iron plate, then the iron comes off of the plate, the hydroxides are provided, the iron hydroxide then precipitates onto the particles. That's what causes the coagulation. So here is a way to do coagulation without the chemical injection. So that alone would be of interest, but the thing that I was most interested in reading the stuff that that Judd and Scott provided is that it significantly lowers the concentration of other things, like the things that really caught my attention were the free oil and grease, the biochemical oxygen demand, because organics can be a big problem with biofouling and organic fouling of RO membrane, and phosphates usually is something that can increase biofouling, the presence of phosphate. And then really interested in the potential for silica reduction, because our options for reducing silica to go high recovery on high silica water are limited. So that's again why I've asked these guys to come through. Then I've got just a couple of slides here that talk about how these things are removed, but we don't need to go into that for this particular presentation. So again, this is an emerging technology. You're not going to find a lot of this in front of RO unit right now. So we need to evaluate, and we're hoping to get some of that information today, evaluate this technology. So at any rate, Judd's now going to provide the information that he has prepared for us, and let's find out about this technology called electrocoagulation. Judd?
Good morning. Thank you very much for having us on, and thank you, ladies and gentlemen, for attending this webinar. So we're going to, before we get too far in the details, I want to just do an overview, if you will, of what we're able to do, and David did a very good job at explaining some of the things we do. So the pretreatment capabilities are vast and wide, and we won't read all of them, and you can look them over. And again, you're going to get a presentation tomorrow, and you'll be able to look this over in more detail. So a lot of these are can be a big problem for fouling membranes, and EC has been used for many years as a pretreatment. Let's see, okay, here's a 50 gallon per minute PAL water electrocoagulation unit. Just to give you an idea of some of the sizes, we have sizes ranging from 1.5 gallon per minute up to 2,500 gallon per minute, and you can use multiple sizes to treat any amount of water you really want to. We have a power supply, logic controller, automatic polarity reversing, excuse me, and we'll explain how that works later to help keep fouling on the blades. We reverse the polarity to help with that, as well as air sparging underneath when the water comes up through the blades. So we convert AC to DC. EC works best between pH of 4 and 12, and it removes contaminants with carbon chain 6 and above. So if you have simple sugars or methanols, those type of things, those are going to have to be treated differently, and we'll get into some studies we've done with adding hydrogen peroxide to the problem before EC to help with a Fenton's reagent or reaction to help with those smaller carbon chains, but we'll get into that at a later time. So the water comes up through the plates, goes over a weir into an overflow, and that water that goes into the overflow, the contaminants are made separable from the water, so that separable constituents and the water goes into a secondary separator where the contaminants can be then separated from the water. Here's a 600 gallon per minute unit. So the water comes up from the bottom through the plates vertically into the patented chamber, and direct current is applied to the first and last blade, and the untreated water comes up from the bottom, comes through the plates, and the water is dispersed evenly and moves upward through those blades, and the water conducts the electricity throughout the chamber. And you can see the weir to the right, the water then goes to the weir and goes to the secondary separation. So the metal blades react to the current by releasing the metal ions, and the electron-flooded water then destabilizes the contaminants, and so then it overflows again to go to secondary separation. But the heavy metals in particular are precipitated into an oxide sludge that will then pass the T-clip test, making the sludge non-hazardous. That's really important, and metals are one thing that can really cause havoc with membrane systems. So let's look at the sludge comparisons between EC and chemical coagulation, for example. So the pH range is typically between 6 and 7. The metals, again, are in oxide form. They do not leach into landfills. They pass the T-clip test, and there's 83% less solids than that with lime softening. And the EPA evaluated that, came up with that number. And the sludge is also hydrophobic, so it's 76% improved infiltration rate. And that's a direct comparison with chemical coagulation. Of course, you have all those chemicals that you have to then take out of the water that you put in. So you have large volumes. It's difficult to dewater because the sludge is hydrophobic. And the metals stay in a hydroxide form, so it can't be disposed of in a regular landfill. Here's an example of a bench test unit that we can take around and treat and test water for individuals. If people have labs that they can test the water, we can run it through the EC, test it, do several runs, and really optimize this operation for on an individual basis. And we can oftentimes, or most of the time, we can extrapolate the results we get from this test unit into larger commercial units. So some of the removal mechanisms, we won't read them all, but there's several for the EC. And depending on the type of water that comes through, you may use one or all of these mechanisms to treat when you're treating the water. So the EC handles a mixed waste stream, and all at the same time in one pass. You can remove fog or colloids, metals, bacteria, pharmaceuticals, emerging contaminants, a lot of different things in one pass. It makes it very convenient. So we optimize the PAL EC by blade type. David did an excellent job in explaining how the blades are sacrificial. They go away, you replace them. They're very easy to replace, so you can use aluminum, iron. People have used titanium, copper, stainless steel. A lot of different ways to, depending on the water you have to treat. We change the amperage density, that's all controlled. The voltage, flow rate, process time, if there's constituents that may take more time to get out of the water. Say selenium may take a 2-minute residence time than a regular 1-minute residence time. We can find that out with the test unit that we use. The conductivity of the water is very important. The more conductivity you have in the water, the less cost for electricity and that type of thing. You can control the pH, raise or lower the pH on certain constituents. And of course, there's different ways the coagulated solids can be taken out of that water. So we're going to go through a few case studies. Mike Mickley with Mickley and Associates did a report for the Office of Naval Research. And it's a 64-page report. So there's just a couple slides that kind of narrow it down. And the goals of the research were to demonstrate the removal capabilities of EC and to find the best application of the technology within the context of pre-treatment to reverse osmosis. So his conclusions were the EC equipment is very simple, and this coupled with a high efficiency made it a strong candidate for pre-treatment for both military and municipal membrane systems. So the summary on his report, the studies also demonstrated that EC lowered the fouling level of oil and water emulsion solutions. That's another important one that Dave brought up earlier. Here's a slide of HAB, or harmful algae blooms. The algae are actually blue-green cyanobacteria. They have characteristics of both bacteria and algae, of course. We had 99% removal of cyanotoxins, so we, in one step, can lyse the algae cell and capture the toxin that comes out and remove it all in one system. And on the right, there's a salmon farm we worked with that had nets that they had to dip in copper sulfate to keep algae from growing on the nets. But when they got done, the TSS was very high and copper. They had to remove the copper from the nets, and we were able to remove 99% of both TSS and copper from those. Another situation, a cooling tower blowdown, or a cooling tower, they needed silica removal. And so they also wanted to go towards zero discharge. On the left is the electrocoagulation chamber. On the right are UV or UF membranes in a holding tank. So the facility consisted of a combination of electrocoagulation, ultrafiltration, a clarifier, a vacuum clarifier, and reverse osmosis. The silica started at 110 milligrams per liter, and we were able to get 97.8% of that out. following the EC, UF, clarifier, and RO. The starting phosphate was 6.6 milligrams per liter, and it was reduced less than detection limits. This is the layout of the El Paso Electric Company. The vacuum clarifier PALs that they built, their clarifier is on the right, and of course the EC units and the ultrafiltration on the left there. Another project we were involved with was WPX Energy on the western slope. They had frac flowback water and production water they wanted to treat, so they used EC in front of UF and then to RO, and they wanted to be able to put their water, treated water, into the Colorado River. And so that was a pretty substantial project we took on, and they took on, actually. So what they did is the Colorado regulates 260 parameters, and you can see what parameters they hold, they ask for. And the EC and the RO and UF were able to have all these requirements met, and they were able to pass the wet test, the whole effluent technology, and the water met an SAR requirement of less than 3 to support downstream agriculture. So that was a very successful project. Another group we worked with was Intel and Arizona State University, or I'm sorry, University of Arizona, and David showed the reactions that the blades show very nicely. So you can look at this when you get your PowerPoint tomorrow. We won't go into that, but the cathode and anode reactions are on this. And so the University of Arizona, their results were TSS, calcium, magnesium, very high removal rates, plus they had some radioisotope contaminant that we were able to remove at a very, very high rate. This project was done by Hayes and Sawyer, and it was a chrome 6 treatment, and they treated with chemical coagulation and electrocoagulation. And a lot of their associates, their PhDs, and they were involved. The contact there is Eric Dole, and his number's at the bottom. If you have any questions, you're welcome to call him. So this spent brine project, they removed 99% of the chrome and uranium and 12% salt brine, and they were able to get 60% removal of selenium at higher EC doses. Again, this is a big project, and you can find out more. You can contact Eric Dole with Hazen. This chamber we used more blades than usual, because anytime you have a very high salt content, the conductivity is going to be very high, so you need to spread the electricity out over a larger period of a larger area on the blades. It's a surface area reaction. So here's the untreated brine on the left, and you have unfiltered treated brine. Very nasty looking stuff, of course. And you have filtered treated brine, and then you have the solid waste that's left over from here. Another Hayes and Sawyer project, they did an alternative, they evaluated alternative technologies for indirect potable reuse in Florida. So this was a really good pretreatment for to RO, and all their PhDs and a lot of very good researchers from Hayes and Sawyer worked on this, and again, Eric had a part of this as well. Their results showed that it removes, the EC removed nutrients, organics, color and hardness, most, if not all, the emerging contaminants and micropollutants and personal care products and that type of thing. And they achieved a 99% ortho phosphorus removal. Another project was Colorado Springs Utility. We've done quite a few things with them. This one was a fluoride removal in their water treatment facility. We've also worked subsequently with fluorocarbons, PFCs, and we have some good results with those as well. But this one was for fluoride removal, and they were at a fluoride level of 4 milligrams per liter, and they needed to get it less than 2, and we achieved that very nicely. And plus, they had a lot of good coliform bacteria and heterotrophic bacteria removal, and their filters worked very nicely because the EC treated water dewaters very nicely. So there's some of the conclusions, the results. They're conventional water treatment technologies coupled with electrocoagulation with aluminum blades. This is a good example too of aluminum blades work well with getting rid of fluoride, but metal plates don't. So you have to use, you have to know which blades to use depending on the water you're treating. We have ongoing research at the Colorado School of Mines. This is just a quick photo log of we did some synthetic compounds were put into the water. So as we mentioned before, electrocoagulation does well with water that has carbon chains 6 and larger. We do a very good job. Every now and then, if you have carbon chains that are less than 6, we can add this hydrogen peroxide to the system and drive the reaction down and get a lot of shorter chain carbons out along with the larger carbon chains. But the idea is you're going to have a lot less sludge produced with this operation. Just another couple pictures of our treatment process when we're doing, when we go to the facility, your facility, we can do this setup. But you can see how the flotation separation occurs just after a couple minutes after treatment with electrocoagulation. Eventually, those particles at the top will settle. The air bubbles go out of the water. Stuff settles. So you can see how easily the solids are separated from the water. And then in this case, in our test unit, we use 11 micron filter to filter things through. And the particles are big enough now that they can be stopped with a filter, and you can see the clear water in the bottom. So here's some typical contaminant removal rates. Again, we won't go over all those. But you can see calcium, magnesium, very good removal rates. Silica, phosphate, TSS, zinc. All those contaminants can cause problems with fouling with RO, so this is a good alternative. This is a 50-gallon per minute system that was installed down in Oklahoma. The efficiency and cost savings of the PAL EC, it's efficient because the water flows in the same direction as the air bubbles float. So you don't have pressure or everything just goes to the top. The savings are because the blades are standard metal stock. You don't buy them from PAL. You can if you want, but you can purchase them in any standard metal shop. They can cut them for you. That's the cheapest. So you don't have any bolts or gaskets or specialized fasteners needed in the system. The cost. Capital cost versus operating cost. So this is a typical, this was a 2,500 gallon per minute EC system versus chemical coagulation. You can see that the capital costs are virtually the same. There's a little difference there, but the operating costs, which you're going to be paying month after month after month and year after year after year, those savings really add up to be able to pay back the operating, the capital cost of the unit very, very quickly. Capital costs, again, as you break it down with equipment, installation, engineering, contingency, process contingency. The engineering costs less, but then you get to the operating cost, and you can see electricity much less, operating labor. It's not labor intensive at all. Chemicals, much less chemical use. Consumables and sludge disposal is one of the biggest things. The sludge does not have to go to a hazardous landfill. So to look at to go over the benefits again, to kind of wrap this up, very high removal rates and a lot of different contaminants. It's adaptable for seasonal operations. We're in areas, sometimes we have to treat, during rainy seasons, we have to treat more water, and in like mining situations, we may have to treat more water. We can do that. We can run a lot more water through the chamber. To get the same contaminant removal rates, we just increase the electricity some until we get down to the normal operating range that's going to be optimum for that particular use. It's flexible. It's quick. You can quickly change operating parameters. It is skid mounted, and there's limited chemical usage. The EC system kills viruses, cysts, coliform bacteria, emerging contaminants, cyanobacteria. There's a whole range of things. It produces 83% less solids in the sludge. The sludge dewaters 76% faster. Passes T-clip tests. No hazardous waste disposals. And reduces the cost of expensive chemical agents. It also eliminates operator transport personnel exposure to dangerous chemicals. Here's some YouTube videos that you can look at your discretion when you get this PowerPoint. Those will be available to you to look at any time. I encourage you to look at them, and we thank you for your time on this. And at this point, we're done with our presentation and we're ready for questions.
All right, thank you, Judd. And I mean, thank you for a good presentation and very quick. I've got to commend you. That was a lot of information in a very short period of time, which is going to allow us to have a lot more time for question and answer. So since we have some extra time, I think I'll just give a little wrap up of what I learned from this presentation. And as I mentioned, I received quite a bit of information from Judd and Scott prior to this webinar, because I didn't know anything really about electrocoagulation other than the name, but hadn't been to a facility that used it, didn't know much about it. So before we would be willing to give a webinar on it, wanted to make sure that this was a technology that looked like it was worth taking a look at. Again, emerging technology for our pretreatment. But as Judd showed in this last presentation, I mean, they partnered with Intel and the University of Arizona. That paper was phenomenal, and I probably got more out of that paper than anything else. But also the mine applications, and Mike Mickley's a friend of mine, and they had partnered, Mike had done an evaluation of that. So when I saw that, some credible people, and Hazen and Sawyer, I mean, they're some leaders in the field, when I saw that there were others that were looking at this, then it was, okay, we've got to put this on our emerging technology list as a potential pretreatment for RO. So again, the thing that I'm hoping to see more of is we see more pilot tests, and Judd and Scott can perform those. So if some plant wants to test their water, they can do that and see what electrocoagulation would do. But again, I've dealt in consulting for the last 30 years, and sometimes you come up against some just really nasty waters, like when you have oil and gas frac flowback, produced water that you want to reclaim and either use it for a recharge of a river or some other beneficial use. The fouling of the RO membrane can just be extraordinary, and it's usually organic bio. And to see that at least certain organics are apparently effectively removed by the electrocoagulation. So that was of interest. I've also consulted at a couple of mines where you have an open pit and rainwater gets in these open pits and just dissolves, the periodic table. And you have high metals, and then they're trying to get rid of this water and reclaim it for beneficial use, and they're using reverse osmosis and UF, and you're having a chemical clean once or twice a week, every RO unit. So it's, so that was another application where heavy metals could potentially be precipitated and removed and reduce the fouling. And the last one that I'll mention is the silica. Because right now, if you look at even 10, 15 years ago, if you had high silica feed water, whether it's a well water or wastewater, we're basically just having to limit recovery. So you may be limited to 50, 60% recovery on your RO unit because there wasn't a whole lot we could do with silica. And then, I don't know, 10, 15 years ago, introduced these silica scale inhibitors. And that allowed us a little more. So, it was hard to tell. Sometimes if you had high iron in the water, then you might not get the results that you would hope for. You couldn't go as high on silica saturation as you could if you didn't have the high metal content. So here is a pretreatment technology, a potential, like I said, emerging that would possibly be of great interest to see in certain applications, to see if it could be used for silica reduction. That maybe would then allow us to go to higher recoveries at lower costs. There is a system like the HERO, the high efficiency reverse osmosis, where you soften the water and then raise the pH very high because silica becomes very soluble at a high pH. But there's cost associated with that, so it would basically be, all right, is this electrocoagulation, would it beat out something like the HERO system on cost for removal of silica and allowing us to go to very high, it could be 90% or higher recovery rate on the RO unit. So at any rate, I just, since Judd was so nice as to give us a few extra minutes, I thought I'd just give you a rundown of what I got of the presentation. And again, you'll be given a PDF. You'll receive it in the mail tomorrow in a thank you email. So all of that information that Judd showed, you can then review at your leisure, and you can contact Judd or Scott. And just one last time, in case you weren't here at the very beginning, David H. Paul Inc. does not have any kind of financial relationship with Judd or Scott or their companies. So we are not promoting this. We're not telling you that we've done research and we think you should go out and buy this and we get some sort of kickback. That is not the case. We have no financial relationship, but we were interested in this technology and thought that some of you might be as well. Okay, so we have a full 20 minutes now for questions and answers. So I'll come back after the Q&A, and we have just a quick, just a thank you and a wrap up that'll take 30 seconds, and then we'll call it quits. So now we'll switch. Judd or Scott will read the question and then give an answer, and then we'll go to the next question. So if you have any questions at all, just type them in to the chat box, to the questions box, and then they'll read it and give an answer.
What are the consumables with the system? Is the aluminum consumed? There are two consumables with the system. One of those is electricity. The electricity is typically used between 2 and 7 kilowatt hours per 1,000 gallons treated. The other consumable is a metal blade. About 95% of the time in our commercial units, that metal blade is aluminum. The next most common is, 95% is iron. The next most common is aluminum, and then a combination of iron and aluminum. The iron typically dissolves at a rate of about 0.2 pounds per 1,000 gallons treated. The aluminum dissolves at about 0.1 pounds of aluminum blade per 1,000 gallons treated. One of the advantages of electrocoagulation is it will make fine colloidal clays or silts separable from the water. When you pass the electrocoagulation charge, the electrons through the water, it will cause those clays to destabilize and clump, and they will clarify or settle out rapidly from the water. Another important prospect is it will remove the phosphate ions and the silicas, which are turned into a form that will not harm the membranes. You may have noticed in that picture of the electrocoagulation unit earlier going directly into ultrafiltration membranes. It coagulates those particles large enough that it will reject the silica, the algae, the phosphate, which were then removed from the reject water using clarification. One important combination about that is that the reject water from the ultrafiltration is totally recovered so that there is no water loss during that part of the operation. Because the silica and the phosphate are removed, that allows us to run a high recovery RO. In that particular case, we were using 1,000 psi membranes, and we were able to increase the total dissolved solids to 70,000 parts per million, which allowed us to recover 95% of the water. And for that particular location, it meant that their existing evaporation ponds were able to evaporate all of the reject water, allowing them to go to zero liquid discharge. One of the advantages of electrocoagulation as a pretreatment for reverse osmosis is that it covers a wide variety of items that can, for example, when reverse osmosis is used for frac flowback water or produced water, the electrocoagulation unit will coagulate the guar gums and the chemicals that are placed in the fracking process. The electrocoagulation unit will make those separable along with oil, phosphate, silicas, allowing, once those are separated, then it allows the reverse osmosis unit to function properly without being destroyed by the oil, the colloidal clays, the silicas. Do we have case studies that show operating costs for different applications? The answer to that question is yes. We have case studies reaching clear back to 1988. So we have a long track record with the electrocoagulation process and the effectiveness of separation. One of the big advantages of the electrocoagulation process is that it is a non-additive process, which means you put electricity and iron blade to the water, but you do not add a second ion. For example, if they use ferrous sulfate, the ferrous would be involved with the removal of things from the water, but the sulfate would continue to build up. By using electrocoagulation, you do not add the sulfate to the water, which means you do not have to remove the sulfate later, or it does not build up when it is reused. Of course, if you do not add those extra chemicals, that means that it does not labor the reverse osmosis unit to separate them, which allows you to effectively obtain a higher recovery rate with your reverse osmosis process. One of the questions was, does this work with a tertiary treated reuse water from a wastewater treatment plant? The answer to that question is yes. The electrocoagulation unit has the same percentage of removal rate from items in the parts per million range as it does in the parts per billion or even parts per trillion range. This allows you to simply, the longer the residence time in the electrocoagulation unit, the lower you can remove those types of metals, and you can take them in essence down to whatever level that you want to. This has been demonstrated by the Department of Defense in treating uranium water, and when they wanted to remove that uranium in the low parts per trillion range. Does the blowdown